In this video, we'll explore the Noetic Math Contest and explore many interesting problems from past contests. So first of all, what is the Noetic Math Contest? The contest for elementary school and middle schoolers, and it's great for beginners to competition math. There's 20 questions, 45 minutes, and they have 2 contests per year. And they have many awards as well, like top 10, 50 for individual and team. And I participated in this contest when I was in 4th grade, and I found this certificate from then. So that's kind of interesting. Also, so for preparing for the Noetic competition, there's many ways resources you can use. So of course you have the Mastering AMC8 book, all the other series on this channel for elementary and middle school, so AMC8, MOAMs, all those series will help with Noetic as well. Because that's the good thing about competition math is it's universal. There's nothing vastly different about this contest as compared to other contests, because all these contests rely on the same general principles. And more resources you can use are the AOPS books as well. And also you can look at some past tests from Noetic. You can find them on their website. And also they have this program called Challenge Math Online. If you're interested in that, you can go to this link. It will be in the description. Okay, so now let's explore some interesting problems from the Noetic Math Contest. And here's some many interesting problems that we have here. So starting off with this one. In the subtraction problem below, the same letters represent the same digit, and different letters represent different digits. What number does ABC represent? So the first thing to notice here is B. So generally, B minus B is 0. So would this just be 0? Would this just be 0? No, not necessarily, because we also could be carrying over, right? So when we're subtracting here, we could be carrying over, and now this would not be 0. So the question is, when we subtract C minus A, do we have to carry over or not? So if C is bigger than A, let's say C was 9 and A was 3, for example, then we wouldn't have to carry over. But if C was less than A, then we would have to carry over. So now the question is, which is bigger, A or C? We look at the left side over here and we see, A minus C. This difference is positive. And this 3-digit number starts with A, and this one starts with C. So A has to be bigger than C, otherwise this difference would not be positive. So therefore C is less than A. And that means we have to carry over. So we can write this as, cross out this B, we can make it B minus 1, and we can make this C 1C, which is, well, really we're just talking about C plus 10 here, right? That's what 1C is. Like 13, for example, would be 3 plus 10. So C plus 10, and then now we're subtracting A to get B. So there's not much more we can do here based on just this, so maybe let's turn our attention to the middle column. B minus 1 minus B. So we of course have to carry over, because B minus 1 minus B can't be done. So we make this A minus 1, and we make this B minus 1, and then plus 10. And that's B plus 9. So then this difference will be 9. So this A equals 9. Oh, and now we know A is 9, we can kind of plug it back here, because we know that this thingy is 9, and this thingy is 9 as well. Because of this condition, same letters represent the same digit. So if A is 9, then we see we have 8 here, because A minus 1 is equal to 8. So we have 8 minus C equals C. C is 4. So C is 4 now, we know, because 8 minus 4 equals 4. And if C is 4, then C plus 10 over here is 14, right? Because this is 4, this is then 4, and then when we increase it, when we carry over, this becomes 14. And then 14 minus 9 is 5. So now we're looking for ABC. That's just 954, and that is the answer to this question. This is a really cool problem where the main thing is just there's basically like 3 kind of columns we can focus at. And the thing is just focus on the column where you can extract information from. We looked at this column, then this column, then this column, and we kind of just kept saying, oh, where can we get more information? And eventually, we just deduced that, okay, C has to be 4 from A equals 9. And then after that, we see we can plug it in here and get that B is 5, and then we have our answer. So a cool puzzle. It's a non-standard type of problem. And now let's move on to the next question. Harry has 6 number beads from 1 to 6. How many different ways can she place all 6 beads in a row so that the sum of any 2 beads next to each other must be 5 or 7? Seems very daunting, right? There's going to be so many cases. So how should we approach this? The key thing is to look for extremes in this case. Look for the most restricting aspects of this. 5 or 7. So let's take a look at the number 6. If there are numbers around 6, like let's say there's a number to the left of 6. 6 plus this number has to be 5 or 7. So what can this number be? Well, clearly the sum of 6 plus this number can't be 5. It has to be 1. Are there any other numbers that could be next to 6 besides 1? No, because any other number, for example 2, would produce a sum 6 plus 2, 8, too big. So only 1 can be next to 6. So what else does that tell us about 6? It has to be at the end, one of the ends. So it either has to be at the right end or the left end. So 1, 2, 3, 4, 5, 6. 2, 3, 4. Right end or left end. Okay, so now let's take a look. Okay, 6 and then 1. What has to be next to 1? Well, the sum of 1 and 6 is 7. So the sum of 1 and this 2 number must either be 5 or 7. And I'm just going to focus on this case for now, because you see this case is basically just a mirror image of it, right? You just flip it. So we'll just focus on this first case and multiply by 2 at the end. So 1, the sum is 7. This sum has to be 5 or 7, which means this number has to be 4 or 6. But it can't be 6. We already used that. It has to be 4. And now we keep going here. 4. What can be next to 4? Well, this number has to be 3 or 1. But 1 is already used. So it has to be 3. Okay, 3. It has to either be next to 2 or 5. 2 or 4. Because 5 minus 3 is 2, and 7 minus 3 is 4. But we already used 4. So then this has to be a 2. And finally, this is forced to be a 5, which we see does indeed work, because 5 plus 2 is equal to 7. So we see we just have one way that works over here. And therefore, our answer is just 1 for here. And then, of course, we mirrored it again. So we got one more case here. So 1 plus 1, 2 is our answer. A really cool problem because it at first seems super daunting, right? 5, 7, there's so many cases. But then we just follow the handy strategy of look at the most restricting aspect. In this case was 6. We know 6 has very, very few options of what can be next to it, right? That's better than starting at, let's say, 2. Because then we'd be, where can 2 go? And can 2 be next to 5 or 3? There's just so many possibilities here that it's very hard to approach it. But for 6, we know there's exactly 1 or 2 possibilities, right? Right end or left end, and we know exactly what number must be next to it. So there's very few cases to work from, and that makes it easier for us. So now let's take a look at the next problem, which is a cool geometry question, or algebra maybe, as we'll find out later. Linda has 1 square rug and 2 identical rectangular rugs. She arranged them in 2 different ways and took 2 measurements as shown below. What's the side length of the square rug? So let's just say the side length of the square is S. So S, for same thing here, right? S. And let's say the rectangle, let's say it has base and height. Let's just say short side of the rectangle and long side of the rectangle. So short side, long side. Short side, long side, short side, long side. Oh, I just realized I overused a variable, so I'm just going to call it width and length. You don't want to use the same variable twice. Okay, so now let's try to use these conditions to form an equation. So 258 equals length plus this part over here, which is, what is this part equal to? It's equal to S minus W. So L plus S minus W is 258. Now similarly, we have 138 is equal to S, or it's equal to W, plus this part, which is S minus L. And we're asked to find the side length of the square rock. This is weird. We have 3 equations, but only 2 variables. So there's no way we can solve this. What are we supposed to do now? Key thing is, we're not asked to solve for all 3 variables, just S. So is there any way we can maybe eliminate both L and W at once? Go to L here, a minus L here. A W here, a minus W here. So let's just add them together. 258 plus 138. Now a neat little mental math trick you can do is 260 plus 140 minus 2 minus 2. And that is 398. And that's equal to, 396, right? 260 minus 2 plus 140 minus 2. That's 400 minus 4. And that's equal to 2S. So S is just 396 divided by 2, 198. So cool problem because of the fact that it seems confusing, right? You got 3 variables, 2 equations. But we noticed that we nicely canceled them out. So it turns out this length and this width could be anything, and we would still get the same answer. That's kind of cool because standardly you would not expect that the length and the width of this thing would not affect the result whatsoever. Let's now explore how to solve this problem. There are 3 drawers. The top one is 9 circle stickers, middle 9 triangle, and the bottom 9 square. How many ways can you pick 3 stickers such that all 3 are different letters and different numbers? So we have 3 different letters to begin with. We have an A, B, and C. And we have 3 different numbers as well, 1, 2, and 3. And they're all different letters must be chosen. So one of them has to be A, 1 B, and 1 C. Similarly, one of them has to be a 1, 1, 2, and 1, 3. So basically, we need to match up this A, B, and C to this 1, 2, and 3. Now, how many ways are there to do this? Well, it's just 3 factorial, but the reason, if you know, is because the A has 3 choices, right? It can be a 1, 2, or 3. We just say, let's say it's a 1, that's 3 choices. Then the B can be 2 choices, 2 or 3. And let's say it's a 3. There's 2 ways where you can choose it. Arbitrarily, let's pick the 3. Let's say we picked that we matched B with 3. And then at the end, C has 1 choice, has to go with 2. That's times 1 way. We have 3 factorial, which is just, okay, how many ways are there to match it? Or this is kind of how where the 3 factorial comes from. 3 times 2 times 1 equals 6 ways to match up A, B, and C, and 1, 2, 3. Now, based on what we have chosen, we have to pick an A1, a B2, and a B3, and a C2. But the thing is, we have to pick 1 from each drawer. So we cannot pick A1, B3, C2 all in the same drawer. They have to be different. So now, how many ways are there to do this? Well, again, you can do the same thing, imagine, top, middle, bottom, and A1, B3, C2. And again, like this thingy doesn't really matter. This is just the case we picked, but it would be the same thing if we had A2, B1, C3, for example. So this is literally the exact same scenario. We have 3 choices for which drawer A1 can go to. Let's say we pick top. Then now we have 2 choices for which drawer B3 can go to. And then finally we have 1 choice for where C2 can go to. So again, we have 6 ways to match the 3 the three things we chose, the I don't know, number letter combinations we chose, and the three drawers. So overall, we just have 6 times 6 equals 36 ways. Because 6 choices to figure out the three number letter combinations we're going to have, and then 6 choices to match those up to the three drawers, because one has to come out of each drawer. And we end up with a final answer of 36. Next question. The letters P, Q, and R represent different digits. The product of PP and 99 is PQ5R. What 4-digit number does PQ5R represent? So PP times 99. Well, 99, and here's the thing, you're looking for patterns here. It's not just a random number. It's 100 minus 1. So naturally, we should think about it as PP times 100 minus 1, which is 100 times PP minus 1 times PP, which is, we know this is equal to PQ5R. So PP00, let's write it out in a standard way. PP like that. We know this is PQ5R. Cool. So notice how P here is preserved, but this one gets reduced. Why? Because we, of course, have to carry over in order to do 0, 0 minus PP. So let's just say we make this P minus 1, right? We have to make it P minus 1, and then this becomes 10, and then, of course, we make this 9 so that we can make this 10. So essentially, now this is what we have to deal with. P minus 1 becomes Q. So we know Q is really just P minus 1, because when we carry it over, this has to be P minus 1. Q equals P minus 1. And now we have 9 minus P is 5. So P has to be 4. And then here we also have 4, because P is the same everywhere. So that makes R 6. And we have P is 4, so we know this thingy is 3. And this P over here is 4, and this P over here also has to be 4. And similarly, Q is also 4. And therefore, we see our answer, PQ5R, is just 4, 3, 5, 6. So the key thing here was realizing 100 minus 1, and then PP00 minus PP, which we can then see by subtracting, by just using our standard subtraction tricks. But here we notice that, okay, we have to carry, so this becomes P minus 1, and then 10, and then 9, 10, after realizing our carrying. And then we can just solve for Q, for P and R, and then finally for Q, and we get our answer. Okay, finally, this is our last problem, or no, it's not our last, second to last problem. In square ABCD, point E lies on segment CD, and F on AE. CE is 1/4 the length of CD, so let's just say this is X, 3X, because 1/4. AF is 1/3 the length of AE. What's the ratio of ABFD to ABCD? So AF is 1/3. So let's say this is Y and then 2Y, right? We're looking at area here, and there's a very standard, useful technique, which is same base, same height trick, basically. And we notice here, Y to 2Y. So we notice that this is a very cool thing to realize. We draw the height here. Now imagine we kind of rotate this. I know it's hard to do here. Imagine we rotate this. The area of triangle AFD is Y times the height divided by 2. And the area of triangle AED is 3Y times the same height. So the ratio, and this symbol over here just means area. AFD over AED is, well, Y times H by 2 over 3Y times H by 2, which is just 1/3 because it all cancels out. So, what about this triangle over here? So we can do the exact same logic, but in this case, we'll look at the ratio of the area to B. We can do the exact same logic. We have the ratio of AFB to AEB. Take a look. Again, we can draw the altitude here. Let's call this h2 because we don't want to use the same variable again. It's going to be different height. We get that this will be equal to y times h2 divided by 2 over 3y times h2 over 2, which is again just 1/3. So if the ratio of this part to this part is 1/3, and the ratio of this to this is 1/3, then the ratio of this whole quadrilateral to this whole region is also just going to be 1/3. We're asked to find the ratio to ABCD. So let's see what we can work out here. We have ADFB to ABED, right? That's just this thingy to that thingy is 1/3. But then we also have that now if we can find the ratio of this to the ABCD, then we'll be able to easily figure out our answer. So what's the ratio of this to ABCD? Well, the key idea is now we use this condition of 3x to x. Notice that this triangle are we given that this is a square? We are indeed given it's a square, although I'm not sure that's really needed in this case. We have the ratio, we have BEC area is half times 4x times x. And the area of ABCD is just 4x times 4x. As you can see here, this is 2x squared, and this is 16x squared. So BEC is 1 over 16 the area of ABCD. So if this part is 1 over 16, it's going to be 1/8 the area of this because it's 2x squared, 16x squared. So BEC is 1/8 the area, and that means this part is going to be 7/8 the area of ABCD. So the ratio of this quadrilateral to this is 1/3. And then the ratio of this quadrilateral to ABCD is 7/8. So our product is just 7 over 24, which is in this case B. So that is our answer, B. Let's now take a look at the next question, which is the final question. This was the last problem on last year's grade 8 contest. So theoretically, it should be the hardest problem, but we'll tackle it. How many 4-digit integers are there whose digits multiply to 90? So naturally, the first thing we want to do is prime factorize 90. We have 3 squared. We have 9 times 10, which is 3 squared times 2 times 5, basically. We have 4 digits. So the idea here is to focus on the most restricting thing first. So 2, I mean, 2 can it can go anywhere. That's the problem, right? It can go here, it can go with a 3 on top, or it can go on its own. Let's focus on 5, because 5 is the most restricting thing here. Because let's say we put 5 here. Now, let's say this digit has a factor of 5. It can't have a factor of anything else. Because let's say we put a 2 here, now this digit is 10. If you put a 3 here, it's now 15. That's not a digit though. Digit has to be less than 10. So we know 5 has to be a digit on its own. And now we just have 3 left. And we have to distribute 3 squared times 2. Let's just say we have 4 choices for where the 5 goes. Next up, do we want to focus on the 2 or 3? And here it's kind of like, which one is more restricting? Because always you want to put the restricting one, focus on the more restricting one. Will give us fewer cases. But it's like, 3 squared, you have 2 3s. 2, you only have 1 2. So naturally, it's probably better to focus on the location of the 2. So let's just say we put a 2 here. Of course, it's symmetric, right? We have 3 possibilities. There's 3 choices for the 2. Now we have 2 3s we need to put. And this is where it gets a little bit tricky. We've got a few cases to deal with here. So let's say case 1. Both of these 3s could be on different numbers, or they could be at the same number, like both factors of 3. Let's say both factors of 3 in one digit. And what does that mean? That means that digit is going to be 9. So 5, 2, and then we can pick any of them to be 9. So 9. That's just, there's 2 ways to do that. And then this last digit will clearly just have to be a 1. So in this case, we've got 24 possibilities. And now case 2, and this is a little bit harder. Both factors of 3 in 2 digits, so 2 different digits. Okay, so what does that mean? We have 5, 2. That means both of these 3's have to be on different digits, and where can they be? So this 5 is locked, right? We cannot add any additional factors here. Now, where do we add these factors of 3? Well, we can add a factor of 3 to this 2, because that will still be 6. But another thing I forgot to mention is we can't add both factors of 3 to the 2, because that would make it 18, right? So we can only add both factors of 3 to one of these 2 digits. But we can add one factor of 3 to the 2. So that's kind of one of our subcases here. We can add one factor of 3 to the 2, and then we can pick any of the other 2 digits to have the remaining factor of 3. So this gives 4 times 3 from earlier, and then times 2 ways to pick which digit gets the remaining factor of 3. So again, 2, that's just 24. But the other case is the 2 doesn't get the factor of 3. So both of the other digits each get a factor of 3. So we would get something like this. And in this case, we would have 4 times 3 times 1, which is 12. Overall, we have 24 plus 24 plus 12. And that is 60, our final answer. And just to clarify here, this 5 and 2, of course, we picked arbitrarily in the beginning, but that's by multiplying by 12 for the places the 5 and 2 can go. And that is our answer, 60. A cool problem that seems scary because there's so many cases, but we break it down and we do the most optimal thing by choosing the 5, realizing that nothing else can go with the 5. And then after that, it's just a few cases, 3, so it's not that bad, and we figured out our answer. Hope you enjoyed this video. I recommend you check out the links in the description to find out more about the Noetic Contest, how you can participate in it. And thank you for watching.